Okay, folks, continuing along. So in this lecture, I'm going to talk about temperature dependence of reactants, and I'm going to introduce the concept of elementary reactions. Okay. So in the temperature dependence of reactions, hopefully this is somewhat familiar to you from your Gen Chem days, but if not, that's why we're going through it. Okay. So as it turns out, in the temperature dependence of reaction, there is what we call an activation energy. Okay? And here what you can see in this reaction, this is an example of an exothermic reaction. And the reason why I know that's an example of an exothermic reaction is because if I look at the potential energy of my reactants and the potential energy of my products, right, I can see overall that would give me the delta H of the reaction. Okay? And in fact, what I would really get, I drew that incorrectly. It would also include the heat released from the top of the transition state. Okay? So what we call right here is our transition state, and that's often given a double dagger, okay, for the transition state. So it's some unstable complex that forms and then quickly decays off to products. We're going to get into this whole transition state in a lot more detail in the next coming sections. Okay. So, but EA, that is our activation energy. And it's related to collisions, for one, and the frequency of collisions. And if those collisions, if there's strong enough collisions to knock that transition state into products, then the reaction will proceed. Okay. So the amount of available thermal energy, so the temperature of a reaction, is really important to activation energy. And so reactions that have this type of activation energy can usually be overcome by running the reaction at a sufficient temperature, or by providing some source of activation energy. So for example, in a combustion reaction, we often have to light it, right? We often have to spark it to get it to go. Okay, so that's related to our activation energy. So I don't have a figure for an endothermic reaction, but if I were to draw this for an endothermic reaction, okay, with potential on the x-axis and progress of reaction, that's Z, okay? Then it would look like the following, just the reverse of that profile, okay? So reactants and products. But now our activation energy is much larger. The activation energy is actually that entire bit, okay? The delta H, on the other hand, however, is actually less than the activation energy in this scenario, okay? So let's see here. So now we know that the activation energy is related to the molecular partition function and the Boltzmann distribution, okay? So that's something goes like this: Ni over N total equals E to the negative EI divided by K Boltzmann T, okay? So EA represents the minimum energy needed to initiate a reaction, okay? And so really what that means is the exponential term gives us the fraction of molecules that can react. So I'm not going to derive this here. We might derive this later on in the semester if we have time. But if we base this off this partition function, then we come up with the following, that a rate constant, K, equals what I'm going to call the frequency factor times E to the negative EA divided by K Boltzmann T. Or A times e to the negative EA divided by RT, depending on the units. All right? So it's the same form as the molecular partition function. So this exponential really is giving us the fraction of molecules with sufficient energy to overcome the activation energy. Okay? So this A is called the frequency factor. Okay? And what you imagine now in the limit, so as EA approaches 0, then e to the 0 is just 1, so then that means K approaches the frequency factor. And that is what we call an extremely fast reaction. So in other words, if there is no activation energy, or if the activation energy is very small, then K equals the frequency of collisions. Okay, so we'll say frequency of collisions. So in other words, every molecular collision leads to a reaction. All right? In the event that we have a large activation energy, not every collision will lead to a reaction because not every molecule has sufficient thermal energy to overcome the activation energy. That's why it's based off this population. Only a certain fraction of molecules, because we recognize the Boltzmann distribution tells us some molecules will be very fast and have a large kinetic energy. Some will be slower and might not have enough kinetic energy. Okay? But if that's the case, if either the temperature is very, very large, right, because 1 over temperature would make this tend to 0, okay? Or if the activation energy was very small, then K just proceeds at what we call diffusion limited. So in other words, the only amount of time, which I will start referring to as the rate limiting step, is the amount of time it takes for the reactants to come together and react. Okay? And so A, for a first order reaction, we know that K is 1 over seconds, so A will be 1 over seconds for a first order. In a second order reaction, we know that K is molarity per second, so that means A will also be molarity per second for a second order reaction. So K and A will have the same units. All right? And so we also recognize if I rearrange this equation right here, okay, if I take the natural log of both sides, then what I get is the natural log of K equals negative EA divided by RT plus the natural log of A, and that's exactly what I've got right here. Right? If I did several different experiments where I changed the temperature, which we know will change the rate constant because at different temperatures, the activation energy, or excuse me, I shouldn't say that. The activation energy stays the same, but at different temperatures, rather, if we increase the temperature, we know that we are making this exponential approach that of 0, so the reaction gets faster and faster. Okay? And also we recognize the slope will be negative EA over R. And it's important to note that EA is always positive, so whether we have an endothermic or exothermic reaction, we'll always see this in our expression. Which, by the way, we call this, I didn't say this, we call this the Arrhenius expression, or the Arrhenius equation. And believe it or not, Sven Arrhenius was the very first Nobel Prize winner in chemistry for this work. Okay? And so now if we play with this a minute, I think I said this already. Yes, so more or less I said this already. I was just looking at my notes. So as E approaches 0, or as T gets very large, K approaches that of the frequency factor. Okay. So now I've got this cool thing going on in this model, so I want to take some time to show you what I got going on in the model. And right away, I'm going to go to the manipulate feature on this model here, which you're going to do. Okay. And let's first turn everything off. So let's say we'll go to room temperature, okay? And I'll explain what I got going on here. We'll say A is 1 molar. I'm going to completely turn off the activation energy, and we'll leave it at a sufficiently large frequency factor, and that sufficiently large frequency factor is just maybe related to a large concentration. Okay. And so now what you're looking at this, you might not be able to tell what's going on here, but with no activation energy, the reaction is so crazy fast, you can't even see my reactant on this profile. So let's take the activation and energy way up, okay? And I'm going to take it up so high now, so that's like 70 kilojoules, that look, nothing is reacted, okay? So we said A initial is 1 molar, and look, there's no reaction, okay? And this is awesome. Look, at 298 Kelvin, with the 70,000 joule activation energy, with the 70 kilojoule activation energy, and whatever this frequency factor means, okay? It's not enough to make a reaction, right? So how can I make this react? Well, look, if I turn the temperature up, and I mean, I'm cranking the temperature on this reaction. Look, I've just taken the temperature up by nearly 100 degrees, more than 100 degrees, still no reaction. So let's keep going and going and going. There we go. Look at that. I have to get this reaction, with the 70,000 joule activation energy, 70 kilojoule activation energy. I have to take it up to like 600 Kelvin to get it to react, okay? But now look what happens. Let's suppose at this temperature and this condition, instead, what if I turn down the activation energy? Well, if I turn down the activation energy, look, you can see the reaction is now getting faster and faster. And so if I go to something more reasonable, maybe let's say 19 kilojoule reaction, at 600 Kelvin, this reaction is over with very, very fast. And so now I can do the reverse. I can turn the temperature down so I can cool down the molecules, right? And as I cool them down, the reaction gets slower and slower and slower to the point where it doesn't react anymore. Okay, so this is a very, very cool model. And I'm going to take some time here describing how I come up with this model, because the code for this gets pretty complicated. So the first thing that I want to walk you through is just getting the rate laws. Okay. So I'm going to do that on another piece of paper here. So we'll say Model 5 rate laws. Okay, so you notice that I've got it as 2A. I added some stoichiometry to this to make this a little bit more interesting. 2A goes to 2B plus C. And so here we're going to assume this is an elementary step, which I haven't talked about yet. But basically what that means is with elementary steps, the stoichiometry does give us the reaction order. Okay, and I'm going to talk about that next, but for now we're just going to go with this example. Okay, so now how do I get the rate law for everything? Well, I'll first start by just following our process by saying negative 1/2 dA dt. Okay, equals. And it's all about the reactants, right? So I only have one reactant, so that's going to be K times A. And in all of these models, you can assume these are elementary steps, which means the stoichiometry does give me the reaction order. And so that means it's K times A squared. Okay. And now this is the only reaction involved in A. So that's it. That's the rate law for A. So I could now, what I'm going to do here, okay, I'm going to keep this in terms of dA by dt. So I'm going to call that negative 2 times Ka squared. All right. And so now with B is going to be positive 1/2 dB dt. And that is actually still going to equal K times A squared, because it's all about the reactants. And so what this means now is dB by dt equals positive 2K times A squared. And that makes sense because the stoichiometry, they both have the same stoichiometry. They should be equal and opposite rates. And then finally, C is just going to be positive dc by dt also equals Ka squared, right? But now that just remains as dc dt equals positive K times A squared. So what we can see is A and B will be produced at a rate that's twice as great as C. And that's what I did right here in my model, in the ND solve portion of my model. Look, there's A of prime t equals negative 2 Ka times K squared. B prime equals 2 times K times A squared. But now C just equals K times A squared. And look, this is what we get in the model, right? You can see that twice the amount of B is created as C because of the stoichiometry. So make sure you're getting the stoichiometry correct. That's really important. All right? And then now to do this manipulate model, this is going to be hairy for a lot of you. So we recognize here I put in Ka and I put Ka for the Arrhenius is A times the exponential of negative Ea divided by RT, where I've got values for R. Well, R is going to stay the same, but I've got values for T, A, and Ea. So now to make a manipulate out of that, like I did here, right? I go manipulate, plot, evaluate. And again, we're going to evaluate this for A, B, and C. And then we're going to replace those evaluations with the ND solve model. But now check out what I do. A prime of t equals negative 2. And then look, this whole chunk right here is K. So we're putting the Arrhenius equation directly in to that model. So there it is, K times A squared. And then here's B prime of t equals 2 times, once again, K times A squared. Okay, and then C, I don't have to have the 2, right, because of the stoichiometry. And then now, look, on my manipulate model, I'm going to vary A, the frequency factor. I'm going to vary the initial concentration. I'm going to vary the activation energy. And I'm going to vary the temperature. And what I recommend, because it's 1 over temperature, that is why I did not start at 0, as I can't do 1 divided by T. You can definitely start the activation energy at 0. That's fine. And I also did not start the pre-exponential factor at 0 either, although I suppose I could have. Okay, so that's how I get this model. Pretty cool stuff. Okay, where now what's happening? Why is this? Oh yeah, I froze the reaction out. So, and you can see this is also a very fast reaction based on the rate constant, right? 10 microseconds. But again, that gives you this idea, right? That, you know, at room temperature or at 100 Kelvin, I know that was a wild value. So let me start over. For 19 kilojoule, room temperature is definitely sufficiently high to make this react over like 1 microsecond. Okay? But for that same 19 kilojoule activation energy, at 100 kilojoules, it's not, or at 100 Kelvin, it's not changing. All right? Okay, so I'm going to now introduce the concept of elementary reactions, finally. And hopefully that will help you connect to some of these other models here, particularly model 3. This is the interesting one, okay? The first model for a simple first-order mechanism, okay? So in elementary reactions, I'll set up by saying, suppose we have the simple mechanism, okay? A reacts and forms some intermediate. And it's a stable, unstable intermediate, okay? And that reacts with rate constant Ki. Well, that intermediate is unstable. So it quickly forms the stable product, okay, at rate constant Kp, okay? So now if we were to add up these two reactions, it just looks like A goes to products at rate constant K, but we have no idea what the order is. So we don't know this reaction order. But for the elementary steps, we do. And the elementary steps, the reaction orders will always be the stoichiometry. But that's only true on the elementary steps, okay? And here's why we don't know what this order is. Because if, let's suppose that both Ki and Kp have similar rates, then that means these reactions are in competition with each other. And that means we won't get a simple first order, second order, whatever for the main mechanism. However, let's suppose another condition, okay? Let's suppose this first step is very slow, okay? And this last step is very fast, which most of the time this is going to be the case in a mechanism like this, right? If this intermediate is unstable, it's not going to be formed quickly. It's going to be formed very slow. And if that intermediate is unstable, it's going to quickly decay to products, okay? So if this is the case, then the rate of this second reaction doesn't even matter, okay? So if Ki is much greater than Kp, then the reaction just looks like A goes to products with rate constant Ki, right? It's like that second reaction doesn't even matter, okay? And I won't write Ki just to avoid confusion. I'll just write K, because that is now what we would view in our experiment. If this intermediate very quickly decayed, we wouldn't even be able to detect it. So it would just look like we have a first order reaction. And the reason why it would look like we just have a first order reaction is because the rate of that very first step is Ki times A, and we know that this was a first order step, okay? If, let's say, for example, this second step was a second order or a third order or whatever, it doesn't matter. If it's extremely fast compared to this first step, then the total reaction order is just going to mirror that of the slow step. So the slow step is rate determining, okay? And so when we have these types of reaction mechanisms where there's one step that's very slow and one step that's very fast, our kinetics becomes quite easy to work out, right? We do the method of initial rates, like I showed you back in the very beginning, and that would give us the total reaction order. However, okay, if our mechanism is complicated, so if our mechanism has several steps, which most of the time that's the case for chemistry, okay, then the issue becomes now we don't get a simple reaction order, okay? We're going to have to do the whole mechanism. We're going to have to look at the kinetic time step in the mechanism, okay? And I've got another video that I recorded several years ago now that's going to get into this on the steady state approximation and consecutive elementary reactions. It's going to continue along with this. I don't want to re-record that, so it's going to be a little bit different than this format that I'm recording in now. So use all of this open space on these slides to follow along with that, okay? But what I want to show you here is when I go through that video, try to make that connection to this model 3, because I mean, I know I wrote A, B, and C, but it's the same mechanism. A goes to I, and then I goes to products, okay? So follow along with that. That's going to help you put these rate orders together. Obviously, I've got it up here so you can pause this and look to make sure you get it right. But what I want to show you here on the manipulate feature of this, on this mechanism, this gets pretty cool in our simple mechanism. Okay, so the first thing that I'm going to do here is turn off the rate constants. Okay, and let's just put in like maybe, I don't know, something easy, like 1 molar or something like that. Okay, so there's roughly 1 molar of A. So I've turned off the rate constants, so there's no reaction. Okay, so now if I turn up K1, K1 only makes the intermediate, right? So in this reaction, A is the A, B is the intermediate, and C is the product. So if I only turn on K1, I don't make any product, I'm just making intermediate. But now watch what happens as I turn on K2. Oh, look at that. So now C is my product, okay? And now I'm going to do this. I'm going to put them like both in the middle, actually, okay? Great. Look at that. So this is, I'm going to show this to you in the video, the next video. This is kind of a special point. This is in particular when the two rate constants are the same, okay? You notice the intermediate is produced but then goes away. And that owes to a maximum, a local maximum of the intermediate where the concentration of A and B are the same. That's in the limit where these two rate constants are very similar. And that's where this would get complicated to see what the overall rate law is. Okay? So, but now if I turn K1 way down, watch what happens. Okay, if I make K1 very slow and I make K2 really fast, this is what we call the steady state approximation, which is going to be the next video you'll see. And we call it the steady state approximation because now the intermediate B is just being produced at this steady state. And what that gives us is it looks like the reaction is just a first order decay in A and a first order production of C, right? We don't get this complicated time profile. It just looks like this thing right here. A goes to products. However, like I said, when both of these rate constants are very similar, so as I turn down K2 and I make it approach that of K1, the reaction becomes much more dynamic, right? Especially something like that, right? And definitely this region in here, that's not exponential. I know my eyeballs aren't perfect, but I can tell you through my experience that now the profile of C and A are not this simple A goes to products. The mechanism is quite dynamic. Okay? So we can only look at the total reaction order and say what the order is if we can definitively say what the rate determining step is. If we can't definitively say what the rate determining step is, then we can't just simply look at a reaction and use the stoichiometry to give us the reaction order. Okay? But definitely in the elementary steps, all elementary steps, the reaction order is the stoichiometry. And we have names for all of those things, okay? So a first order elementary step is called unimolecular. And it's first order because there's only one molecule. It's that simple, right? Like this. These are all simple unimolecular steps, okay? A second order reaction we call bimolecular, okay? Because two molecules are involved, right? And then finally, when we go third order and beyond, we call that termolecular. And in the coming weeks, I'm going to talk about third order reactions a lot. They're very interesting. As it turns out, reactions that are driven by heat in their fundamental mechanisms, there's almost always a termolecular step. So this is with respect to like explosions and combustions. Within the mechanism, you don't see it in the total reaction, but within the mechanism, there's almost always a third body, a termolecular body. in those mechanisms. So they are not straightforward mechanisms. Okay? Okay, great, folks. So watch that last and final steady state approximation video. And make sure you go through it, because that's really, this steady state approximation video, there's also an example of how to do a mechanism. It's really going to be key for you getting your project off the ground and started. Okay, folks, so after that video, that'll wrap it up for this first part on kinetics. Okay, I'll see you later.